Hey guys, lesson 3, math 30-2 for exponents and logs. So it says modeling logarithmic functions. Yesterday we did modeling exponential functions, but today we're going to look at logs instead. I realize right now, oh, I'm not on pen. Maybe it'll let me write in blue today. Live in the dream. We'll see. So this should say, no, it went back to black. Logarithmic function. Oh, I don't have my computer and tablet mode. That's the problem. It's fighting me. So a logarithmic function by performing a regression. Wow. So now we've done linear regressions, quadratic regressions, cubic regressions, sinusoidal regressions, exponential regressions. It's time for logarithmic regressions. So on the first day, we would have seen logarithmic functions in this form. So y equals a times the log base b of x, where b is greater than 0, b cannot be equal to 1, and a cannot be equal to 0. So this part here, so the way that your calculator is actually going to spit out a logarithmic regression is in the form y equals a plus b times, so now instead of log, it says ln of x. So I'm going to say it like the word ln, and what it actually is it's the natural log and so it's kind of saying important. So ln x is actually, so ln again is ln, log is log. So the ln of x is actually the log with base e. So ln of x is equal to log base e, so representing kind of that part there of x. And so what e is, you can kind of think of it, oh, I guess I have it right here. It's kind of like pi. So it's a specific number that's actually quite widely used in math. You've probably never seen it before. It's called Euler's number, and it's approximately equal to 2.718. And again, it's an irrational number, so it will go on non-repeating decimals forever and ever and ever. It's kind of like pi in that it's that we know what pi is equal to. It's a number that comes up a lot in math. You don't need to know the specifics of what it is, but it's actually looking at, it's the value of 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, on and on and on and on and on. So just know that when we're talking about the natural log, which again, you'll hear me use the word ln instead, it's actually just so ln is equal to log with a base of e. So when your calculator spits out this one, don't get too confused that it doesn't look like that original form that we talked about on the first day. Okay, it's missing a portion that's in your notes. So the question, it says, when objects of different mass are compared without a scale, to be perceived, the difference in mass must be large enough. So it's saying if you take two things and you're holding them in your hands, and they have a very small difference in mass, sometimes you can't tell which one weighs more, which has more mass. So it says, for example, when held in a person's hands, masses within 5 grams of 100 grams will seem to be the same. So if I handed you something that weighed 95 grams and something that weighed 105 grams, it would I guess that's what the next sentence is saying. It says they would feel like they probably weighed the same amount. So the 5-gram difference is known as the minimum perceivable difference. So for heavier objects, the minimum perceivable difference increases. For various masses, the table is shown below. So again, if something has a mass within 5 grams of 100 grams, you won't be able to tell the difference if you have like one thing in each hand. So when we get up to 200 grams, now it's 10. So that would be, I could give you something that weighed 190 grams in one hand and 210 grams in the other, and it would all feel the same. At 400 grams, it's 15, so it would be 180, or sorry, come on, Tanya, do math. 385 to 415 grams, those would feel the same. And then up to 800 grams would be 780 to 820, those would feel the same. So again, the minimum perceivable difference for that. And so this data set that we have can be modeled by a logarithmic function in the form y equals a plus b times the ln of x. So in your calculators, this little chart, put it into list 1 and list 2. Now I need to remember I wish I had a calculator with me. I think the way it says it is log reg. I don't remember what number it is. I'll write it down on, never mind. I see in my notes actually that I have it as ln reg. I'll write a little note in my notes to make sure what number it is in the Casio and what number it is in the TI. So perform, man, I can't talk right now, this type of regression. So it says determine a logarithmic regression to model the data. Round the values of a and b to the nearest tenth. I actually have a bone to pick with you guys. You guys just love ignoring when I give instructions like this. So think about what I'm asking you, and especially for numeric response questions, right? If it says to the nearest tenth, please do that. Don't round it to the nearest whole number or the nearest thousandth. It says to the nearest tenth. Okay, so I'll give you a second. You might want to pause the video and do the regression. So what I have down, again, without a calculator to verify that previous Tanya was as smart as current Tanya. So y equals negative 28.2 plus 7.2 times the ln of x. That's what comes up. So again, to the nearest tenth. Hopefully I rounded those right. So that's your logarithmic regression. And it says based on the regression equation, determine the minimum perceivable difference for a 2100 gram object to the nearest whole gram. So thinking about what that is, so again, when we put it into L1 and L2, this is x and this is y. So now we're going to have is an x value equal to 2100. So you could absolutely graph this in your calculator. So there is a button somewhere on there that has the natural log there that you can put it in, or you can do log base e. But, sorry, I'm confusing myself now. I would probably just substitute it in. That's what I personally would do, because that's easier than trying to graph it in the calculator and then find my graph. So 28.2 plus 7.2 times the ln of, so now we know x is equal to 2100. And so you might need to put an extra set of brackets in your calculator to make sure all of this stuff happens before. But what we get is y is equal to, I think it gives me 26.87 something. So to the nearest whole gram would be 27 grams. So the minimum perceivable difference would be 27 grams. Or again, if you don't want to sub it in here, like we did, you can put that equation into your y1 and graph it, and then trace when x is equal to 2100. Okay, so another question here. Again, a lot of these are big word equations, lots of gobbledygook stuff going on, but the thing is, there's always this chart. So, well, I don't know that there will always be it, but in these ones, you see a chart there. So you should be thinking right away, oh, I can do a regression to figure out the equation, that you don't necessarily need to understand everything that's happening there, but just understanding, like, in terms of the graph, those are your x and y values, and then how you can apply any other questions that they're going to ask you. So the flash on most digital cameras, yeah, that's thinking a little more old school, require a charge capacitor in order to operate. The percent charge, which is Q, remaining was recorded at different times after the after the flash had gone off. So the flash duration represents the time until the camera has 50% of its initial charge. The flash duration also represents the length of time that the flash is effective to ensure the object being photographed is properly lit. So the first thing it's asking, do a regression, right? So to model the data. So round the values of A and B to the nearest 10th. Again, it's asking you specifically for that. But then I notice when I do it to the nearest hundredth. Let's just even change that because 10th is not going to be a good thing. So pause the video, give it a try. So the regression that I come up with, y equals 0.46 minus 0.10 times the natural log of x. I think this number is like a really long decimal. So that's how I got 0.10, because if we're going to nearest hundredth, well, I'm dropping a value that's going to round it up, so that's going to round this up. So that is our logarithmic function that represents the data. It says use your model to determine the duration of the flash to the nearest hundredth of a second. So now you kind of need to go back to the question. So it says the flash duration represents the time until the camera has 50% of its initial charge. I promise you, it's so hard to write here. That's why it's messier than is usual. So 50% of its initial charge. So again, what we're looking at now is Q, which is again is equal to X. So I'm saying Q based on this chart here. So Q is equal to 50%. So you see it's going to be somewhere in between these two values, right? Between 0.05 and 0.09, because it's between 60 and 40. It's not going to be like exactly halfway or anything convenient like that. So Q is equal to X is equal to 50, right? So again, you could do it graphically. You could have your graph and trace when Q is equal to 50. What is Y equal to, which represents, again, your time. Or you can sub, so you can do it graphically. Or you can substitute into that equation that we wrote for part A. So again, you might need an extra set of brackets there. so I get 0.0691. Says to the nearest hundredth of a second, equals 0.07 seconds. So 0.07. Yeah, it's in that range. It's right in the middle, actually. I said it wasn't going to be right in the middle. Technically, it's a decimal, but that's okay. Oh, I've gone back too far. There we go. So 0.07 seconds is the duration of the flash. And C, same thing that you could do graphically here. So probably if you did B graphically, it's pretty easy to do C graphically, but I'm just going to keep doing the substitution way. Oh. So it's asking when will the flash have 10% of its initial charge? Is that 0.23 seconds. So make sure you're punching stuff in your calculator as well. All right. I actually really like this next one. So caffeine is found in coffee, tea, and soft drinks. Many people find that caffeine makes it difficult for them to sleep. I'm one of those that if I have coffee too late, I have a difficult time going to sleep. So the following data was collected in a study to determine how quickly the human body metabolizes caffeine. I do this every time that I start to panic that I'm not actually recording, and I have to always go look. I'm good. All right, so each person started with 200 milligrams of caffeine in their bloodstream, and the caffeine level was measured at various times. So at time 0, they had 200 milligrams of caffeine in their bloodstream, and they looked at the level during various times. So after 1 hour, after again being at that 200, they had 168 milligrams of caffeine in their blood system. After 5 hours, well, we're not even down to half after 5 hours, right? 113 is still greater than half of 200. 6.5 hours, all right, we're at least under a half. And 20 hours, again, and so on. And 20 hours, it's down to 18 milligrams of caffeine in their blood. So first things, you don't have to understand any of what's going on here to do part A. You just need to be able to put in your L1 and your L2. So again, representing X and Y, and perform the regression. So pause the video for a second, perform that regression. Says to the nearest 10th, I guess, and I'll put mine up in a second. All right, so your regression, so I think this one was 43.85976 or something, and this was 8.2908, so to the nearest 10th, just one number after the decimal. So 43.9 subtract 8.3 times the ln of x. And again, x is representing the amount of caffeine in the bloodstream, and y is representing the time. Okay, so we have a regression equation. So it says now determine the time to the nearest 10th of an hour. It takes an average person to metabolize 50% of the caffeine in her or his bloodstream. So like we said, it's somewhere in this range, right? So to metabolize 50% of it, so if we started with 200, we're looking for when 100 is. And so it's not just as easy as being like, yeah, I don't know, it's probably like 5.5, I don't know. You don't want to just guess. There's a way we can figure it out. So what we want to be looking for is when there's 50%, half of the original. So we're looking for 100 milligrams. So So 50% of 200 is 100 milligrams. So we're looking for y when x is equal to 100. Just like before, you can do it graphically, or you could substitute it in. So again, x is equal to 100, so I'm going to substitute in a 100 there. And so what I get, I don't remember if I used these rounded decimals or the original ones that we had, but I get to the nearest tenth of an hour, 5.7 hours. And so that, again, does make sense because it was somewhere in the range of between 5 and 6.5, so we're happy with that answer. So it takes about 5.7 hours to be at a level of 50% of the original caffeine. So Paula drank a cup of coffee that contained 200 milligrams of caffeine at 10 a.m. How much caffeine to the nearest milligram will be in her bloodstream at 9 p.m. that evening? So first thing that we need to kind of figure out is how much time is passing between these. So from 10 a.m. to 9 p.m., that's 11 hours. Right? 10 till 10 would be 12 hours. So 10 till 9 is 11 hours. And so this one, this is going to be, you're going to have to do this one graphically. So again, in y1, you're going to put in 43.9 minus 8.3 times the ln of x. And in y2, you're going to put in 11, right? Because if we look back at that chart, too much. Your y values are time, your x values are the amount of caffeine. So if we're looking for a corresponding x value based on a y value of 11, let's go back. You're going to trace the intersect between that. So graph those two and then see if you can find the point of intersection quickly. Pause the video. So just kind of looking graphically, so your second line is going to be this y2 line. I made mine dotted. So your point of intersection is going to be at y equals 11, x equals the nearest whole number, 53 milligrams. So after 11 hours, she'll have 53 milligrams of caffeine still in her system. Oops. Is there one more question? Oh, I didn't have it on here, but I think I have it in the notes. It says, Paula is only able to sleep if her caffeine levels are below 40 milligrams. So we know that this one, she wouldn't be able to sleep because her caffeine level is still too high. So by 9 p.m. that evening, she wouldn't be able to sleep, right? So it says, if Paula usually goes to bed at 10 p.m., so she wants to go to bed at 10 p.m., what is the latest time that she should drink a cup of coffee? So again, we're looking for when x is equal to 40. What amount of time are we looking at? So y equals 43.9 minus 8.3 times the ln of 40. Again, we're substituting in x equals 40 because she wants her x value, if we look at the chart, which is the amount of caffeine equal to 40 or less. And so that gets us, I don't know if I rounded that, but 13.3 hours. And man, I'm going to be so technical. So 13.3 hours is not 13 hours and 30 minutes. 0.3 of an hour is 18 minutes. Right? Because 0.5 of an hour would be 30 minutes. So 13 hours before 10 p.m. because again it says she wants to go to bed at 10 p.m. So 13 hours before that is 9 o'clock a.m. And then, so that's 13 hours before. So if we wanted another 18 minutes before that, Paula, this is so silly. Paula should have her last coffee by 8:42. She should be done it. She should be digesting it and have it in her bloodstream by 8:42. So maybe she wants to be done drinking it by 8:30 in the morning. So again, she finds she can only sleep when her caffeine levels are below 40. So she knows her rate of, she knows she's an average person. So her rate would be the same as our equation that we had there. And so she needs to finish her coffee by 8:42 a.m. All right. So just the little key summary. So a logarithmic function may be a good model for a set of data if there are points on a scatter plot forming an increasing, decreasing curve, where the domain is restricted. Okay, so this is the big thing. We would have seen that at the beginning. To the set of positive real numbers. And so general form of logarithmic regression model is, so again, it's going to come out in this form instead of what we were looking at before. So most graphing calculators provide the I don't know why they have this twice, but this is what the equation will look like. So it can be used to predict values that are not recorded or plotted. So things that are not within your data table, so looking at points in between. Predictions can be made by reading values from the curve of the line of best fit on a scatter plot or by using the equation. Again, you're going to want to be using the equation of your regression. I don't think I want this. So you are going to have, if you look over to the next page, there's not practice questions, it's the next lesson. So you must have a worksheet to be working on, an exponents worksheet. So that's what the rest of your day looks like. All right, take care.